Well, now we're going to be starting section 5.4 of your text, which is on more complex experiments. Before we can get into everything they start talking about, first we need to talk about what conditional probability is. So conditional probability, the notation we use for it, we write it like this: probability of event B, given that event A has already happened. And this is the way we talk about the probability of a particular event B happening after another event A has already occurred or has not occurred. Now, when we want to find the conditional probability of some particular event, it makes a difference whether or not the events we're talking about are independent or dependent. So this is another important topic. So first we'll talk about what independent events are. So we say that two or more events are independent if the occurrence or non-occurrence of one event doesn't affect the probability of the others. So some examples of this would be any type of problem where they say replacement is involved, and we'll show you some examples of that in a minute. Also, any type of situation that deals with, something that resets. So like if we roll a die or if we flip a coin multiple times, whatever number you land on the first time you roll a die is not going to affect your chances of getting any particular number the second time you roll the die. Same thing for flipping coins. If you land on heads the first time, that's not going to affect whether you get heads or tails the second time you flip the coin. And then we would say that two or more events are called dependent if the occurrence of one event does affect the probability of the others. Examples of this would be anything without replacement. So let's say we're drawing cards from a deck. We take one card out. We leave it out, and then we want to find the probability of getting another card. Well, we've changed the number of cards in the deck, so the probability of getting anything else after that is different because instead of having 52 cards, you've removed one, now you only have 51. Okay, so now let's go back to conditional probability. Whether or not events A and B are independent or dependent affects the conditional probability. If A and B are independent events, the probability of B given A has already happened is just the probability of B. And that's because the probability, like A having happened or not, does not affect the probability of B, so its probability stays the same. If A and B are dependent, the probability of B given A is the probability of A and B divided by the probability of B. Okay, you're not always going to need to use this formula depending on what the problem is. There are other ways where you can figure out what the probability of B given A is given the context of the problem. And this brings us to something called the multiplication rule. So now if we want to look at the probability of A and B together, this would be the probability of A times the probability of B given A has already happened. And we'll see what we're talking about exactly with this here when we get to some examples. Let's look at an example now. Here we're being told that we have a fair die and we're rolling it twice. Now we want to find the probability that both of the rolls are even. So we're looking for the probability that roll 1 is even and roll 2 is even. Okay. So we're looking for the probability that the first roll is even, and then the probability that the second roll is even, given that roll 1 was even. So we know this using our multiplication rule, but now we need to determine, well, are these independent events or are these dependent events? And this is a situation where these events are independent. Whatever we get on the first roll is not going to affect what we get on the second roll. So our probability that our first roll is even, right, we have the numbers 1 through 6 on the die, and 3 of them are even, so that probability is 3 out of 6. And then our probability that the second roll is even, given the first was even, is still going to be 3 out of 6. Right? We still have 3 even numbers on the die out of 6 total numbers, and nothing to do with rolling the first die is going to affect what we get when we roll the die again. This is actually leads to something called the gambler's fallacy, where certain people might think that if they go to a casino and they keep going to the same slot machine again and again and again, eventually, you know, their chance of winning is going to increase or something like that. And that's absolutely not the case. It doesn't matter how many times you go to the slot machine, your probability of winning is always the same every single time, you know, the lever is pulled. Okay. Right, so we can actually simplify these to make our lives easier. Right, this is just a half times a half. So our final probability ends up being 1/4, right? And let's say we didn't simplify this, right? 3/6 times 3/6. What do we have here? 9 out of 36. Again, that's going to simplify to 1/4. So we still have the same thing. Okay, now let's look at another problem. Here we're being told that a bag contains 10 black marbles, 8 green marbles, and 2 blue marbles. First, we're being asked if 2 marbles are removed from the bag with replacement to find the probability that first both marbles are green, and then to find the probability that the first marble's green and the second is blue. And after we've done that, we're going to look at what this problem would look like if the marbles are taken out of the bag without replacement instead of with replacement. Okay. So first what we need to do is look at how many marbles we have total. So 10, 8 green, 2 blue. Okay. So we have 20 marbles total, so our probabilities are going to, you know, end up being out of 20 at first. We want to now look at the probability that both marbles are green. So this is the probability that the first marble is green and that the second marble is green. So the probability that our first marble is green and our second is green, well, we can rewrite it like this. Probability that the first is green times the probability that the second is green given the first was green. Okay, and now this is with replacement, so these are independent events. Right, with replacement means okay, so these are going to be independent events. Okay, so now our probability that the first is green, well, we have 8 green marbles out of 20 marbles total. So this is just 8 out of 20. Then our probability that the second marble is green, given that the first is green. Now this is with replacement. So what this means is we've taken 1 marble out of the bag. We look at it, it's green, we put it back in the bag, and then we take out another marble. So the amount of marbles in the bag is the same, there's still 20, and the amount of green marbles in the bag is also still 8, because after we took the marble out, we put it back in. So our chance, again, is 8 out of 20. Okay, and then if we multiply these together, we end up getting 64 out of 400, you know, which is also 0.16 or 16%. Okay, now let's see what happens if we want to find the probability of the first one being green and the second one being blue. Well, another way that we could write this is we could say this is the same thing as the probability of the first being green and the second blue. Okay, which we could then again write as the probability using our multiplication rule as the first being green times the probability of the second being blue, given the first one was green. Okay, and again, these are still independent events, so we're still treating our probability that the second is blue as just the probability of getting a blue marble. So our probability of the first one being green is still going to be 8 out of 20. Nothing changed between these two problems. And then our probability of the second one being blue, well, we have 2 blue marbles out of 20 marbles. Again, we replaced the marble after we took it out, so there's still 20 marbles in the bag, but there's only 2 of them that are blue. So we multiply this together, we get 16 out of 400, which reduces, or which we could write as 0.04, which is the same thing as 4%. Okay, so now we'll take a look at this problem, which it's the same thing as the last problem, except now the marbles are being taken out of the bag without replacement instead of with replacement. So the fact that they're telling us is without replacement now, this means that we are now dealing with dependent events. Okay, so the probability that both marbles are green, the same thing that we wrote before, we're looking for the probability, that the first and second are green. Which we can then rewrite as the probability of the first one being green times the probability that the second is green given the first is green. Okay, so what's the probability now? The probability that the first one is green is still going to be 8 out of 20, just like it was before. We start out with 20 marbles in the bag and 8 of them are green. So nothing changes about that. Now when we get over here to the probability that our second marble is green, given that the first one is green, this changes now. So we've removed one marble from the bag and it's not being placed back into the bag. So now there are only 19 marbles in the bag because we've taken one out. And we've taken out a green marble because we're told the first marble that we got was green. So now instead of having 8 green marbles in the bag, we only have 7 green marbles. So our probability of getting a second marble that's green after we've already removed one green marble on the first try is going to be 7 out of 19 now. Okay, and then we can multiply these together and we end up getting 56 out of 380. Okay, and you don't need to reduce your answers. Or maybe you do. I still haven't decided how I'm going to be giving out exams yet. But you don't need to reduce your answers and your homework as long as you show all of the work. Okay. Now we'll look at the second problem where we want to find the probability that the first is green and the second is blue. So again, this is, same as last time. Probability first is green and second is blue. Right? Again, we can write this as probability of the first being green multiplied by the probability that the second is blue, given the first is green. Okay. So our probability that the first marble is green, still 8 out of 20. Right? When we start, again, there's 20 marbles in the bag, 8 of them are green. Now when we look at our conditional probability of getting our second marble being blue, given the first was green, we've removed one green marble from the bag. So we only have 19 marbles in the bag now. But we still have 2 blue marbles because we removed a green marble. We didn't remove any of the blue marbles, and there were only 2 blue marbles in the bag. So this is now going to be 2 out of 19. And then we multiply these guys together, and we end up with 16 out of 380. Okay, let's look at one more problem. In this problem, we're being told we have a standard 52 card deck of cards, and we want to find the probability of drawing 3 face cards. So face cards would be jacks, queens, or kings. So we want to find the probability that we draw 3 face cards, first if the cards are drawn with replacement, and then if the cards are drawn without replacement. So you can pause the video here, you can try and solve it yourself first, and then I'll walk you through the solution. So let's see. First, we'll look at when we're doing this problem with replacement. So if we're doing it with replacement, that signals that these are independent events. Okay, so the probability each time we draw a card out of the deck is not going to be affected by anything that happened before. So first we're going to remove one card from the deck, look at it, put it back, remove a second card from the deck, look at it, put it back, remove a third card from the deck, look at it, put it back. There's always going to be 52 cards in the deck every time we draw, and we're going to have the same cards to, possibly get every single time we draw a card from the deck. So here we're looking at the probability, you know, first card, I guess we'll use F to be a face card, and second card is a face card, and the third card is a face card. So we could rewrite this as probability, the first one is a face card, times the probability the second is a face card, given the first was a face card. And then we have a third thing happening here. You can have more than two independent events. Probability that the third is a face card, given, you know, first and second were face cards. Okay, so now the probability that the first card is a face card, well, we know that we have 4 jacks, 4 queens, and 4 kings in the deck. So this means 12 out of 52 cards are face cards, or this is the probability of getting 1 face card. Okay. So the probability of getting 1 face card, or a face card on the first draw, is going to be 12 out of 52. Now the probability of getting a second face card after we've drawn 1, this is with replacement. So let's say we shuffle the deck, we draw a card. It's either a jack, a queen, or a king. It's any one of these. We look at it, we note that, now we put it back in the deck. We still have 52 cards in the deck after making that first draw, and we still have 12 face cards in the deck. So again, it's going to be 12 out of 52. And same goes for the third draw. Right, we still have 52 cards in the deck because after we drew the first 2, we put them back in. And we still have 12 face cards in there because after we drew a face card the first and the second time, you know, they were put back in each time. Right, so we can also express this as 12 over 52 to the third power. And if we decide to multiply this out, we end up with 1,728 out of 140,608. Now let's look at this problem without replacement. So if we're doing this problem without replacement, now these are dependent events. So again, we're going to be solving this the same way that we solved the previous problem, except now our conditional probabilities are different. So we're still looking at, you know, the probability that the first card is a face card. Then we want the second card to be a face card, given the first one was a face card. And then the probability that the third card is a face card, given the first and second cards were face cards. Okay, so the probability that the first card is a face card is still going to be 12 out of 52, just like it was in the previous example. When we start out, there's 12 cards, there's 12 face cards in the deck, and there's 52 cards in the deck total. So it's still 12 out of 52. But now when we're getting our second face card, we've removed 1 face card from the deck, so there's only 11 of them left, right? We didn't put the card back, and now there's only 51 cards in the deck because we took 1 card out and didn't put it back. And then now for the third draw, right, we've removed 2 face cards from the deck, so there's only 10 left, and we've removed another card from the deck, so now there's only 50 cards instead of 52. So we multiply all of these out, and we end up with this.